designed to handle whatever traffic's going to be on it. And it is obviously beneficial to the environment. It is becoming more and more used in stormwater management. Because of the absence of sand or the small percentage of sand, there is a pretty high void content in this concrete of 10 to 25%, where traditional concrete, unentrained air content is 2 to 3%. If you entrain air, it's going to be 5 to 7%. So as opposed to traditional concrete, where compressive strength is usually the primary acceptance, there's no compressive strength test for pervious concrete. So acceptance is based on the air void structure and the unit weight during placement. And you can see that picture there. It really is like a rice cake, or Rice Krispie cookies, I guess. That's the consistency of it. It's not a proprietary product. Almost all concrete producers in the region make a pervious concrete mix. They all have their own recipes for it. It's placed without rebar, without any metal in it, because water goes through it, the metal's going to be exposed to the water. Still see some designs try to use bars to connect sections, but no metals in it. And typical application is 6 inches for parking lots, sometimes 4 inches for sidewalks. It can be used in a lot of different applications, from erosion control of slopes to parking lots, as we'll see here on this site. Driveways, I think Lowe's, for instance, uses it. A lot of places for their outside garden areas to let the water go through. This is a detail from the drawings for this project for what we're going to see when we go out onto the site. So this has a design of 6 inches of pervious concrete on top of a minimum of 6 inches of number 67 stone. 57 is often used, just an open graded aggregate, so that the water goes through the pervious concrete and into that gravel layer, and then that gravel layer is used for storage, and that's important in freeze-thaw application. This particular design project also had some maintenance requirement notes on it, but sometimes when projects get passed from construction to maintenance, those notes don't get passed along, so we're going to talk about that as well, and the requirement and the necessity for maintenance. There are 4 different test methods that ASTM has prepared. As Dwayne said, I was on the committee that created these test methods. ASTM D1688 is the one test during placement. It's a plastic test. It's a test on the concrete as delivered to the site, and it's for density and void content, and that's typically one of the acceptance criteria for pervious concrete. There are 2 hardened sample tests. One is C1754 for density and void content, and that is after placement of the concrete, taking a core and bringing that core sample back to the lab to test it for density and void content. The other hardened sample test is C1747, which is a laboratory test where samples are made in the lab and tested for resistance to degradation, to give an idea on the mix, how well the mix will hold together, and I'll go through that in more detail. And then there's also one test in place on the pervious concrete, and that's the infiltration rate, and I'll talk about that more as well. For abrasion resistance, you want a strong, dense surface to have a durable pervious concrete surface. And The two primary ways to make sure of that are good curing after placement, immediately after placement, and to have a durable mix. One of the things that's typical in every pervious concrete, to some degree, pavement will have raveling. Raveling is defined by ACI as the wearing away of concrete surface caused by the dislodging of aggregate particles. Because that surface, because it's open graded, there's the aggregates are exposed, and they will come up, and so it's really important in maintenance to make sure that we're vacuuming, sweeping, getting rid of those aggregate pieces so that more traffic doesn't cause those loose pieces to make more loose pieces. But it's expected, so it's gonna happen. Just want to maintain it so it doesn't become worse and worse. As I said, one of the test methods for determining the durability of a mix is ASTM C 1747, and it's something that's not done enough yet and it really should be specified for producers to present results of their proposed mix of this test method. And it's really helpful for producers to compare their mixes and to make more durable mixes. And so I'm going to go through it briefly. Again, the purpose is to provide a durable mix, or to determine how durable your mix might be, and to compare mixes. It's not intended for cores, so this is just a laboratory test where samples are made in the lab, but not to be tested on cores. Oh, yeah. So this is some of the samples. I'll just pass them around for people to take a look at. As I'm talking here, you can see what the result at the end of this test are. So this is the equipment that's needed. Again, it's a specialty lab test. So the first thing you do is you get your plastic density test, your C1688 density, and that's done by mixing a sample in the lab and performing that test on the plastic pervious concrete. You're then going to, by calculation with that density, you're going to calculate how much mass of material you need to fill a 4x8 cylinder halfway to that density. You're going to weigh that out, and you're going to put that into the mold, and then you'll drop the mold 10 times from 1 inch height, and then you're going to use a compaction hammer called a Marshall hammer. Marshall hammer was used in the asphalt testing and made sense to use here because the diameter fits perfectly inside of a 4x8 mold. And you're just going to use that to consolidate until you get it to 4 inches high. So we know the density is the exact same as the density that we tested by the other method. And you're going to put a cap on it, and you're going to make 3 of these. You're going to cure them the same way we cure traditional cylinders in accordance with ASTM C31 at the same curing temperature until they're 7 days old. And at the end of 7 days, we're going to take them out of the mold. We're going to weigh them, and then we're going to put all 3 of them together in an LA abrasion machine. And this is a big steel drum with paddles on the inside so that the samples, as the drum rotates, it picks up that sample and then dumps it back to the bottom. So there's a lot of abrasion action going, and then all 3 of them are in there at the same time. And that rotates for 500 revolutions. We're then going to take all the material out, and we're going to sieve it through a 1-inch sieve, and we're going to then weigh the material that was retained on the 1-inch sieve. And then we're going to calculate the mass loss to determine percent loss. I think you said these samples that are going around were about 20% loss. And that's a really good result. That's a really durable mix. But again, for the producer to make sure to compare that durability with the infiltration rate, you still got to get the infiltration rate. If we did a traditional concrete mix, it would have much less loss than that. So it's a really good tool for that. So again, that's the test for durability. So those are the two key things, durability and then infiltration. And now we'll talk about the infiltration test, which is a test we'll show you when we go out into the field. Anybody bring a ring in with them? No, that's fine. So ACI calls it the percolation rate, ASTM calls it the infiltration rate. Maybe they'll get together and determine which is the right term, but ACI defines percolation rate as the rate usually expressed in inches per hour, which is what we use, at which water moves through the pervious concrete. So the test method for that is C1701. And the purpose is to determine the infiltration rate at a specific location. What it doesn't do, it doesn't tell you if it's a surface test, so it doesn't tell you if the pervious concrete is clogged at the bottom, above the stone layer. It doesn't tell you what the infiltration rate of the soil is below that layer. It's just to tell you what the surface infiltration rate of the pervious concrete is. This is the equipment that we need. And that's just a diagram of the 12-inch diameter ring, which you'll see out in the field to be used. When you're testing it for acceptance after initial placement, the requirements are to test at least 3 tests for up to 25,000 square foot area, and then do additional tests for every 10,000 square feet. Making sure that your tests are no closer than 3 feet apart, and don't test if there's any standing water on the surface, and you're not supposed to test within 24 hours of a rain event. So the first thing you do is just a light broom, just broom off the surface of the area that you're going to test to get rid of any loose pieces on the surface or any debris. And then this is an example of a ring. This is a really fancy one with engraved on it, and this one actually is perfect. It fits on top of a 5-gallon bucket, which is where you're going to hold your water. So this is an example of the ring that'll be placed on the surface. So we put plumber's putty on the bottom of the ring, and then set that onto the pervious concrete surface, and then work that plumber's putty to make sure that when we put water inside, that water doesn't go laterally, that it's going to infiltrate into the concrete. And pass that around. So this is a 2-part test. The first part is called a pre-wetting test, where we'll weigh out 8 pounds of water, and then we'll pour the water into the ring, inside the ring, into the pervious concrete. And we maintain a head of a 1/2 inch. And you'll see when that's passed around, on the bottom of it, there's two lines grooved in and marked in, and that's your 1/2 inch plus or minus range to keep that water level. So you keep a constant head of water. And then you're timing it. So from the time that the water first hits the concrete until you can't see any water on the surface anymore, and you record that time. So that's called the pre-wetting, and that determines how much water you use for the actual test, based on the time it takes for that 8-pound pre-wetting to occur. So if it If that water goes through in less than 30 seconds, then we'll use 40 pounds for the test, 40 pounds of water. If it's more than 30 seconds, we'll redo the 8-pound test. So to do the test, you're supposed to start within 2 minutes of doing the pre-wetting, and you record the weight of the water, whether it's 8 pounds or 40 pounds, and you'll pour the water into the ring, doing the same thing. You maintain that 1/2-inch head on the water, and you'll time it from the time the water hits the surface until there's no water left on. And then you calculate the result. May look like a complicated formula, it's really not. K is a constant just because you're using different, because your mass is in pounds, which is M, your diameter is in inches, which is the D, and your time T is in seconds. So K is just a constant so that you don't have to worry about converting all those units to get inches per hour. If you're doing this for acceptance, then there's a lot of things to put on the report, and if you're getting a report, you should expect to see all of this information on that report for acceptance. The locations, the date of test, how old the pervious concrete is if it's known, what the time was for the pre-wetting test, what the last rain event was, how much water was used for the test, what the inside diameter of the test ring is, how much time elapsed, what the infiltration rate is, and any notes. We did some testing yesterday out on the pervious concrete, and Hassam's got a handout, and Dwayne, to go through what the test results were. So there's a front and a back. On the front it's on our letterhead, so this is an official test result. I didn't put the project name because I didn't have the owner's authorization or anything to say where it was, but just so you know, it was here. And we did testing, the infiltration testing. Initially, the project's about 3 years old. We did initial tests, and then we did some cleaning, which you'll see how they do the cleaning, and then we redid the test. And as you can see from the results, in one area, the test number 1, we quit the test after 10 minutes because the water was just barely seeping into the concrete. It was probably as clogged as a clay. It was acting like a clay. And after cleaning, it was 143 inches an hour. So the cleaning process works really well for a clogged surface. You'll see a couple of tests there where there wasn't much change. It's because the pervious concrete really wasn't clogged in that area to the degree that it was in other areas. And on the back is a graphical representation of those results, just to show the difference. I think you'll see on 5, you can barely see it, but there are 2 test results there. It just wasn't clogged, so there was very little increase. This is an example. If, like I said, that test only tells you what the surface of the concrete infiltration. This is a diagram potentially of a way to test the whole system, all the way through the pervious concrete, through the stone layer, and into the soil. But you would need to have that in place and ready during the whole placement process. So it's not done, but it is if somebody's interested in testing that whole thing. This is to test the subgrade, the soil, to make sure, if it's designed for the soil to infiltrate, called a double ring infiltrometer, test that we do a lot. Some other test methods that may be of interest, there's a standard for random core location. So if there's a dispute, somebody thinks that somebody's only picking the best spots or the worst spots for acceptance, this is a way to referee that and to make those not cores, but the infiltration random. C42 is a coring spec, and C174 for thickness could be used to verify the thickness of pervious concrete cores. I'll take any other questions, but I'll go through a couple of things that we get a lot. A lot of designers try to use the ACI design for traditional concrete and use it for this. Probably put in 3,000 psi. The problem is with pervious concrete, because of the way it's placed, the top surface is a different compressive strength than the bottom, because it's all placed out uniformly, and then it's densified from the top. So the densification process densifies the top surface more than the bottom. So if you take a core, you'll get a really low result because you're only testing the compressive strength of the bottom. You're really looking at the top is what's going to determine, but there's no way for us to test the compressive strength of that top inch or 2 inches.
So when you get a concrete mix design for pervious concrete, what information you should be looking for aside from the moon water cement ratio according to criteria?
Well, the one is that test method for durability that I was talking about, the percent loss. That's really important for durability. And then the other thing is the void content. Yep, go ahead.
The raveling that you mentioned.
You should not be able to make more loose raveling with your foot.
Okay.
No, that after the curing period, which is typically 7 days, it should not happen with your foot. Okay. Then you've got a problem, because it's going to come up. It's going to come up a lot more under traffic. It's typically, the testing's typically done by a third-party independent laboratory, but anybody can do the infiltration. Really, I mean, maintenance departments of public facilities could easily get the equipment and do the infiltration tests just for maintenance purposes. So first of all, oil spills. I mean, small spills, drips from cars, where typically on an asphalt or traditional concrete surface, those are going to run off and go into the stormwater system. But with pervious concrete, because of the way it's open, there are microbes that are within that matrix that live there after it's been installed. And those microbes actually feed on that oil. So you'll get very little oil that will go into the groundwater system. Pervious concrete can become clogged. It gets clogged typically where you've got runoff from adjacent facilities, whether it's other pavements or grass areas. Soil will run off. It can also be from itself, from the raveling process. And that's why routine sweeping that we'll talk about and vacuuming can restore it. Freeze-thaw environments, it is, if it's designed properly and that water is designed to stay in the gravel layer below and you don't have clogging on the surface, it's very resistant to freeze-thaw. It's more resistant to de-icing chemicals than traditional concrete typically, because the water doesn't stay on the surface, but we really recommend against using de-icing chemicals on it, especially in the first year after placement. While it is more resistant, like I said, to traditional concrete, if it's over salted, it certainly could become an issue. You could look at it, it's possible to remove the surface, the top couple of inches, and place a thinner layer of a more durable mix, but typically the whole thing goes out and is replaced if you have early age raveling, or if it's time to replace it. It also could be, you could look at, this is where all of our trash trucks go, and it's a really heavy loaded area. You may decide to redesign it and use a traditional concrete in that drive lane area and let it flow, surface flow into the adjacent pervious concrete layers. What's the lifetime?
20 years plus.
Yeah, I mean, the same as your asphalt and traditional concrete pavements. In talking about the price, it's hard to compare because a pervious concrete pavement system is part of your stormwater system. So to really compare it, you gotta take out, okay, we were gonna put this pond in, how much was that pond and all the piping that goes to that pond, how much was that gonna cost us? Well, now we don't have to do that because we got a pervious concrete parking lot and we're using that as our pond. And so you gotta compare the whole system if you're comparing. So you talk about infiltration of the subgrade. So during the design process, you need to know the infiltration rate of the subgrade, so that the whole system is designed based on that. If the infiltration rate is less than 1 inch an hour, then you're probably not going to use it for the subgrade for infiltration, but you're going to design that system more as a retention system. You may even put a liner between the soil and the stone. You'll design your stone thickness probably for a 10-year storm event, to hold the water there and let it slowly go out through the rest of your stormwater system. So we see that a lot here. We did a project in Leesburg nearby to here where that was the case. The infiltration of the soil couldn't be counted on, so it was basically a pond. Instead of having a separate open pond, the pond is built underneath of your pervious pavement. So if you have more than 1 inch an hour, then you're probably going to design it to account for water's going to infiltrate back into the ground over time. And it may be a combination. If it's right at 1 inch an hour, maybe your design has, okay, some of it's going to go into the ground, but some of this is going to be a retention system too, and go out through a different means. So there's drains that are often put in, sometimes under drains, sometimes over drains at the top of the gravel layer, so that if water does build up to that point, then it can go out those drains into the stormwater system. So it's really important in the design to know what the soil properties are to determine your design. The void space in the gravel layer is at least 40%. The void space in the pervious concrete is 10 to 25%. So the chances are almost none that you're going to get infiltration and carry those fines through the pervious concrete. They're going to stick in the pervious concrete before they go into the gravel layer and clog. Because it's an open graded stone, it's just vibrated into place. Just minimal, really just. Yeah, because if you loose dump it and then put traffic on it, it's going to settle. So basically, you just want to get that vibration on it as you're building it to take care of any settlement in the stone layer. It's typically going to be the top inch. It's just not going to be able to get through further than that. It's really not going to clog more than the top inch.
So after that,
it's just clogged.
Yeah, clogged.
So
Nothing is going down there.
Right. So what happens typically is we could actually see what happened on this project is rainwater was washing soil onto at the top of the pervious concrete area, and that was clogged. But the water just finds the next spot down to go through. And so once you get an area clogged, it just starts to grow outward of the clogging because all of your materials start washing across. Her question is about sloping the pervious concrete. So there's two aspects to it. If you're infiltrating the soil, you want that soil level to be flat. But you can then, so what we recommend civil engineers to do is to have two grading plans. A grading plan for the soil and a separate grading plan for the pervious concrete top. The pervious concrete can be at a very significant slope and still be able to infiltrate. You'll see the project out here, there's a pretty good slope on the parking lot. But the soil is flat. Thanks for all your questions. Thanks.